The next speaker we will hear from is William Olson.
All right, my name is Grant Olson. I'm a senior business analytics student here at Piedmont, and I'm a member of the baseball team, if you couldn't tell by what I'm presenting about today. So I'm going to be talking about our process goals, which are kind of the heart of Coach Scalley's coaching philosophy. He says that if we get our process goals, the results will take care of themselves. So I just wanted to take a deeper look at that and analyze if there was any statistical backing to that philosophy. So this is a picture of our process board that we have in our indoor facility. Coach Scalley always likes to say our opponent isn't in the other dugout, it sits above the water fountain, which is where our board is. So you can see our different process goals, scoring 7 runs, having 50% or more quality at bats, getting 9 or more freebies on offense. So that's drawing walks, stealing bases, things like that. And then getting a big inning on offense, that's scoring 3 or more runs in 1 inning. And then on defense, it's allowing 4 or less runs, giving up less than or equal to 5 freebies. So walking people, hitting batters, making errors, that kind of thing. And then not allowing a big inning from the other team. So not letting them score 3 runs in the same inning. And then throwing less than or equal to 150 pitches for the whole game. And you can see we have some data from this year filled up on the board. So this is just some preliminary data with the records that I have for the last 6 seasons, not including this year. You can see on the graph on the left, I took the average run differential based on the number of process goals we got. So you can see once we hit about 4 goals, we started having a positive run differential, which means that we scored more than the other team. And then on the graph on the right, you can see the wins and losses by number of goals achieved. So you can see at about 4 goals, it's roughly even, but then the winning percentage skyrockets when you hit 5 goals or more. So what I wanted to find out when I was doing this was, is there a statistically significant benefit to achieving these goals? Which goals were the most important? And then could you use the goals to predict wins and losses? So like I said, I got secondary data from Coach Scalley, which I was lucky enough that he recorded every goal from every game for at least the last 6 years. And I imported that data into our studio and ran a series of tests, which the first was hypothesis testing. So it looked at the mean of 2 groups. So I grouped each variable by either the goal was met or not met. So for number of goals, that was 0 to 4 goals and 5 to 8, and it compares the winning percentage in each group. So you can see the winning percentage when each goal is not met and when it is met. And then every single difference in means was statistically significant. So the hypothesis test just shows you that there was a difference. It doesn't exactly tell you why. So that's for the winning percentages. And then I have some graphs here for the differentials. In green is when the goal is met, and you can see the like the dispersion of the run differentials when you have a game where you fall into each group. Then this is for quality at bats and offensive freebies. So you can see the difference in differential there. Getting an offensive big inning and scoring 7 or more runs, you can see the differential. Allowing runs and the number of pitches that we throw. And then defensive freebies and the defensive big inning. So then I ran a regression for the number of goals. So that's just looking at, as you get more goals, does your run differential change? And that was significant with an adjusted R squared of 7.7033, which means the number of goals explains about 70% of the variance in your run differential. And when I did this, I took out the offensive runs and defensive runs allowed, because it's pretty obvious if you get those 2, you're going to win. Because if you get your 7 runs and you don't allow more than 4, that's pretty obvious. So I took those out. And then I ran regressions with each variable by itself, and each one was significant, but the adjusted R squared for all of them by themselves added up to well over well over 1 because there were other variables impacting it. So what I chose to do was a forward stepwise regression, which basically it just takes the most significant variable and then keeps adding the next most significant to the model until you reach a variable that's not significant anymore. So I will get into that, exactly what went into that one in a second, but the adjusted R squared for that model was 0.7832. So that's 78% of the variance in run differential being explained by the goals that it put into the stepwise regression. This is just a chart of the number of goals with the run differential. Those are the data points that are the dots. And the line is the model that the regression spit out. So you can see it fits pretty well. So these are the variables that were the most important for predicting a run differential. The AIC it doesn't really go with anything. It's just a measure of variance. So the lower that number is, the more accurately you're able to predict the model. So the offensive big inning was the most important for predicting differential. Not allowing a big inning was the next, and then getting your quality at bats, throwing a certain number of pitches, and getting your offensive freebies. And all the other goals after that for run differential specifically were not significant. So this just shows exactly how much each variable impacted this regression model. So you can see with a stronger slope, offensive big inning, defensive big inning, those are the strongest slopes, and they kind of even out as you go down. So for predicting wins instead of differentials, because it's not you can't put it on a number line, it's either a win or a loss, so it's a binary variable. So you have to run a logistic regression instead. So I did that with number of goals, which gave me an AIC of 149.41. And then McFadden's R squared is not the same as the adjusted R squared. It's a predictor of how strong of a predictor your model is for what you're trying to guess. And any value above 0.4 is considered a strong predictor. So I did the same thing with the forward stepwise regression here. And it just took, it just kept adding variables until the AIC leveled out, which means that everything after that would not have contributed to the AIC at all. So the variables in this one, the defensive big inning was the most important. Quality at bats was next, offensive big inning, defensive freebies, and offensive freebies. And the other ones, for the purpose of predicting a win, did not produce a significant change. And then again, this just shows the exact impact that each goal had on the win percentage. So using this model, I was able to run a test that showed I was able to tell the model to predict whether we would have won or lost based on the data set. So the model spits out coefficients that you use to insert your actual numbers, and then it'll give you the probability. And if the model gives you a value of 0.5 or more, that is predicting a win, and anything below 0.5 is predicting a loss. So you can see we have predicted losses that were actual losses were 69, predicted losses that were actual wins, 13 games, predicted wins that we actually lost were 20 games, and predicted wins that were actual wins were 119. So the total accuracy of 85.07% is the percentage of predictions that were correct. So the predicted losses that were actual losses, and the predicted wins that were actual wins, divided by the entire number of games. So I took the line that the logistic regression gave me and the regular regression, and I calculated the winning probability of winning and the predicted run differential for certain games this year. So the model is built on things that have already happened. So I wanted to project that and predict what would have happened this year. So inserted our process goals that we got from so far this season for certain games. And you can see the predicted win probability and the predicted run differential. And then the actual results. So you can see for Cal Lutheran number 1, predicted win loss 91%, we won. Predicted differential was up 6, and the actual was 4. And then most of it is consistent, except there was the Brevard game. We had 52% probability of winning with the process goals that we had. We ended up losing that game. Our differential was projected to be about 1, and we lost by 2. And then we have on the other side, we had a 49% chance of winning against Overport. So that should have been a predicted loss, but we actually won. But the differential was still pretty accurate. And then you can see most of the differentials and the win percentages or the win probabilities line up pretty well to what actually happened. So just going through some model integrity to make sure that the data wasn't flawed and that we didn't have any issues with our variables. So multicollinearity, I ran VIF testing, which if you get a value higher than 10, that indicates that you have a multicollinearity problem. I didn't have any of those, but then I ran every variable with every other variable. And that gave me some issues with offensive runs and defensive runs, because that's pretty strongly correlated with winning. And if you get your run scored, you're probably going to have, high QAB percentage, high freebies, that kind of thing. So they kind of skewed the data. So I took those 2 out for the regressions. Homoscedasticity, this is just making sure that our data is pretty evenly distributed, horizontal line, and the data is pretty evenly scattered. And then looking at outliers, there's a little dotted line kind of in the corner. It says Cook's distance. It's not even on the chart really, so I don't have any data points outside of that distance. And if you had any points outside of that distance, that would indicate that you have an outlier problem, and I don't, so we don't have to worry about that. So in conclusion, there is a statistically significant benefit to achieving process goals, specifically 5 or more. For run differentials, the offensive big inning, defensive big inning, quality at bats, pitches, and offensive freebies are most important. And for getting a win, the defensive big inning, quality at bats, offensive big inning, defensive freebies, and offensive freebies were the most important for your winning percentage. The goals can be used to predict wins and differentials with pretty good accuracy. So future research can test different goal combinations. So you could, it's basically what the stepwise did. It's the end result of this. You would test different goal combinations with each other, but the stepwise just gave you the most optimal scenario. And then future research can modify the goals to optimize success. So the issue I ran into with runs scored and runs allowed, that is probably, if it were me, I would probably consider changing those goals because of the impact that they have on the other ones. And then you could also mess around with like the quality at bat percentage is 50%. And you could always just look and run testing to see if that number should be changed, or for the offensive freebies or defensive freebies or number of pitches or anything like that. But I think there is, and it may be that this is already the optimal measurement for everything, but you can always look into it and see if that has any effect. Any questions? All right, thank you.
So that was the last presenter, but if anybody has any questions for any of the presenters, you could ask them, and you guys can just stand up where you're sitting. It just asks that you restate the question to make sure that it's recorded on the Zoom.
Questions, I would think about for setting the process goals just right.
Well, I was gonna ask you, it doesn't account for core coaching, but I don't know the variables.
The 30% of the model that's not.